Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about HART, Isostatic Pressing or HIP. So let's dive deep into it. So what exactly is the problem that we have to HIP it in order to solve it? Well, metal parts are not limited by the elements or the alloy. For example, you might think, oh, I have steel, it would be stronger than aluminum. Not necessary, because all of that can be changed if you do not have quality control. Basically, quality defines how strong something is. So what vectors we have? We have a lot of vectors, but primary vector for this discussion is porosity. Meaning, for example, let's say you have two steel parts, right? Two plates, and somebody is stick welding it and they rushed it. They did not do a proper job and you grinded it, there is voids there. And you inherently know that puppy will break from there because it's not strong, it's not done properly. And same happens when you are forging, casting, things of that nature. If you have too much void or too much porosity, it's bad. Let that be very clear. Porosity bad is just bad. You do not want void inside your material. You want like one absolute solid part. But turns out it's very difficult to achieve. How difficult? Well, most of the time humanity do what we call a casting. You have a structure and then you cast it. But here's the deal, that creates a lot of porosities. Like no matter what you do, it creates a lot of issues because you will have a lot of trapped gases. Generally, these things are not done in a vacuum. So you will have gas that could trap and create vacuum bubbles. Then you will have shrinkage and then you will have basically solid debris. All these things make things messy. Now, let that be very clear. If done correctly, you should not have to worry about it. But if you want to get the best scientifically possible strength, this is not it. And same goes with powdered metal parts. Powdered metal parts are really good, really cheap, mass producible, GG awesome. But again, they are powder. They start as a powder. So they fundamentally, if you look into how much void space they have a lot. So that's also a limitation. And then you come to 3D printing. Inherently the same problem as like basically powdered material. This puppy, because it's you are doing it layer by layer, and again you might can easily understand if you're dealing with layer, but it's not plastic, it's not like one continuous loop. So you have literally every grain boundary that is being basically molten and then solidified. So grain boundary wise, that's also not that great. So inherently we have a lot of technology that allows us to make parts, but if you really want like really absolute strong part, you have to do what we call forging. Basically you go bam bam into it. Now that does work, but it has a problem of basically access. If you are going like this, the grain structure in one dimension would be super strong, others not so much. So we need something that is balanced in all direction. Forging is not that, unless you are forging a cube, then you can keep rotating it. But most of the time we are not forging cubes. So there is a fundamental limitation, not on the element, not on the alloy. We got that part. The chemist has sorted that part out. Like we got this. It's the quality control. Porosity control. Basically we want something that is really low porosity. Like of course you can't have absolute zero, but very close. That's the target. And most things that we do, forging is the next basically closest, but again not what you call mass scalable, so to say. So when we are casting, when we are powdering, or when we want to do complex things like 3D printing, they are all limited. That's the problem that HIP solves. So HIP basically is high temperature and pressure. Let that be clear. It has to have both of these puppies. High temperature and pressure cooking of parts. Now, what kind of temperature we are talking about? So whenever you are putting something into it, let's just say you have an alloy. That alloy melts at 1000 degrees Celsius. Generally, depending on the alloys and the mixture and composition, you will be at 70% of its melting temperature or 95%. Some alloys, specifically ceramics, do require that kind of high temperature. But most of the time, you will be at 70 to 95 degrees Celsius. You do not want it to melt, meaning once you send structures into it, it's a fully formed structure, meaning you're not supposed to do, oh, I did it and now I'm going to do machining and grinding. No, this is supposed to be the last step. You put it there, you use it, done. So fundamentally you do not want to melt. You want high temperature, but not so high that it actually melts. You do not want phase transition. That's the critical aspect. Depending on the alloy mixture, you will always be just below phase transition. Then isostatic. Now this is the critical part. This is what makes it magnificent, is that you have equal pressure from all sides. You do not have the problem of forging where it's like, in one axis is like ultra strong, other axis, no. This puppy is like from all sides, all dimensions. So it's really good. And when it comes to pressure, what kind of pressure we are talking about? Yeah, pressure is stupid. That's all I can say about this. Like to give you a context, we most of us know about basically undersea vessel because of the Titan. You have to understand those things are very hard to test, like pressure vessel and all that. Yeah, that's nothing. That's nothing. Like those are generally 1,000 bars or 1,500 bars. This puppy can go up to 2,000 bars, meaning these things are so robust, like in terms of like raw oomph handling. You can go boom inside it and it's like, did you do something? Like this is one of the most robust sealed structure we built in terms of pressure structures. 45,000 psi. Now let that be very clear. This is the upper limit of what we actually need. Most of the time you're not gonna do this because again, let's say you are a jeweler who is doing this for your basically platinum jewelry, and yes, people do that. I'm really, really hoping that Indians do that. We are popular for jewelry, and if we don't do this, that would be stupid. Basically, because again, most of the jewelry is done by casting, they have a lot of porosity. Now, again, if you X-ray it, if it's a really bad one, you can see it. But if you have high resolution X-ray, you will see a lot of porosity, and that creates a limitation. Basically, the things is not as ductile as it could be. Things is not as shiny as it could be, simply because you have so much void. So every time you polish it, now new void, new void. So it creates an issue. So cooking it is a best way of solving the quality control, so to say. And generally, whenever you are talking about this sort of temperature, you have to understand things react very quickly if you have high temperature and high pressure. So inert environment is mandatory. Now, some people have tried vacuums, and yeah, at that point it goes back to mechanical compression, but we are not talking about that. Most of the time, argon would be used. Second cheap option is nitrogen, but let that be very clear. You have to select certain things because nitrogen is reactive at high enough temperature, and we are talking about high temperatures. So nitrogen only in select alloys. Helium, if it's something like a nuclear industry where it's like, nah, we need top quality, helium would be used, but it's expensive AF. Most of the time, argon, shut up, go home. So most of the time, argon is utilized, and they are the highest rated pressure vessel ever made by humans. Unless there is some very niche case scenario, like if you can make pressure vessel for this, Mariana Trench is like, bruh, please. Like it's not even a worthy problem for you. It's like, bruh. So that's the HIP part of it. So what things go in this ecosystem of HIP? Well, first is giant pressure vessel with a door. Now, the door engineering is the most complicated part because again, it has to close and open multiple times without compromising itself. So basically, it will look like a gun bridge because if you have seen naval guns, they have like giant boom devices, like so big of a boom device, which again, I could not understand how the heck they do not have casings. It's like, oh, they have powder bag. And it's like, what happens to that powder? It turns to poof. So in those sorts of where you have like the giant thing going ka-chunk, yeah, it has doors something of that magnitude, same engineering, so to say. And you are talking about high temperature. Metals become weak when they are exposed to very high temperature. So from the outside shell, you have ceramic heat shield because again, that's the only thing that can handle that kind of temperature. And you're like, okay, what if I use a SpaceX heat shield? They work in low vacuum. They can't work if you have high PSI and 2000 bars. The gap inside them will be filled with gas. It will no longer be useful. So ceramic heat shield is the only thing that keeps the outside wall to be overheated, so to say. And we generally require high temperature. Now, thankfully, we are not planning to melt things inside that. So generally 2000 degrees Celsius is good. Like how would you achieve that kind of temperature? Most electrical resistive element do not work more than that. So carbon, basically graphite. Now this puppy can go up to, in principle, 3000 degrees Celsius. Basically, if you ever want something stupid high temperature, graphite is the cheapest way of doing it. Like, then why don't we use it? It oxidizes, so you do need inert atmosphere. Without it, it will catch on fire. So because you are talking about argon only, and again, a flushing has to be done, then they start sending current to it. So this puppy allows you to achieve very high temperature. Most of the time, most basically HIP modules do not have this because again, most of the time you don't need 1500 degrees Celsius. So most of the time this is overkill. But if you are building, let's say, jet engine turbine blades, ta-da! And then you have liquid cooling of the outer wall because again, you are talking about so much heat energy, and the fact that you have high pressure, it's conducting very efficiently. Like conduction of basically from this heating element to the outside wall is exponentially better if it was just like open to the air. It's like maximum conduction. So you do need a very active cooling in order to handle this puppy. And then we come to the interesting part. How the heck you pressurize something that high? Like, yeah, gas is compressible, cool, awesome, but like not 2000 psi kind of compressible. How the hell you get that? Well, you utilize what we call hydraulic compressor, because if you directly try to use an electrical motor to either do piston compression or do something like that with a mechanical advantage, it will not work. It just will not work. So what we do is electrical pump drives a hydraulic system. That hydraulic system does the actual compression. And hydraulic, because again, you know, hydraulic is like PSI wise, like hydraulic is like, I'm your guy. Like 2000 bars is like, bruh, that's like Wednesday for me. So you use hydraulic compressors in order to achieve the stupid PSI. That's how you push argon into it. So that's what you do. And then you have a lot of valves and switches, because again, they do require energy control, but nothing fancy. Let that be very clear. All this thing is brute force technology. This is made in, like, you know, just after Oppenheimer. Basically, once they realized boom boom is done, they're like, okay, what if we make reactors out of it? So much technology had to be created. This was one of them that allowed fuel element creation. So this technology was made for that. It's not complex. Like that, any Tom, Dick and Harry can do this. Nothing inside it required is like, you know, how or this or that. Even basically hydraulic compressor, that's also a known thing. Nothing in this is complex. It's just brutal. As in, like, you need like big or Soviet Union engineering kind of, like, you know, robustness. This is one thing, like if you cheap out on the steel, it goes kaput. So fundamentally, it's not complex. It's not like lithography machine or things of that nature. Like, this is simple, dead simple. But trust me, there are 200 countries on this planet. Only few countries have know-how of building this. Now we come to the cooking part of it. It's a cooker, pressure cooker, so to say. Huh. It literally is a pressure cooker. So recipe. Now here's the each alloy. Basically, if you are like my teeth, zirconium teeth is going there for cooking, it will have different recipe. If you are sending platinum ring there, it will be different. If you are sending basically jet engine turbine blade, different. ICBM parts, different. So recipe has to be controlled for each alloy. And be mindful, if you have very high porosity, you can shrink the part. So that has to be calculated forwards, meaning jet engine turbine blades, they are generally very high density, very low porosity anyway. Like they only have, let's say, 10% void. 10% void you can send into this, it will not change the shape or structure. But if it's like, you know, 50% void, yeah, then it will shrink. So you have to be mindful of that. And again, recipe accounts for all of that. So generally we start to gradually increase the pressure. So you open the argon bottle that is like barely 100 to 150 bars, and then you flush it, and then compressor starts like, let me apply some hydraulic oomph to it. And then you slowly ramp it up in around 30 to 60 minutes. You take your time, because again, you do not want to shock the system. And then you control temperature ramp up. Now this ramp up has to be done this way so it does not give thermal shock. Now you have to understand, no matter how strong the alloy is, if you give it bad enough thermal shock, it will shatter like glass. Does not matter which alloy it is. So for that reason, we have to gradually rise it, because you have to understand, even if you have an object and you have a very high pressure ecosystem around it, and if you heat it up very quickly, it will take time to heat up from the inside. So you will have outside that is hot, inside that is cold, that will create stress. So for that reason, you want to thermal soak it. It's like easy, bro. And again, you have high pressure. And again, that pressure is the reason why if you have a turbine blade that has a lot of tiny holes, the gas pressure in those tiny holes is what keeping them open without them collapsing. So that's why if you can collapse the void, why the heck it does not collapses the void? Yeah, because gas pressure is there. You have to make sure that gases can go there. Isostatic pressure is maintained. The voids that are generally surrounded by other grain particles, they get collapsed. So you slowly ramp it up, and again, slow temperature ramp up is critical, otherwise it will not work. And pressure is also ramped up, like something like this, like, you know, depending on your alloy, something like this graph would be created. And then you hold it. Once you reach the point temperature, once you reach the pressure, you hold it. Now holding could, depending on the product requirement, it could require like turn it on, come back tomorrow. Like, I'm not even joking, some of them like 8 hours to 15 hours. So you hold the time. Now this is where magic happens. This is where basically pore closures happen. Basically you have giant crystal grains that are awesome, strong, but they are surrounded by tiny small ones. Bad. What happens when you have this sort of plasticity? Basically you have pressure, temperature that is plastic enough, and then these things start to get married together. Basically, instead of hundreds of small units, they start to combine into larger units, and now you have much less grain boundary. So that removes all the porosity, and diffusion bonding happens. So even if you have two grains that are not basically inside each other, because you have high temperature and electron can jump from each other, it does what we call diffusion bonding. What does that mean? That simply means if you can cut it open, look it into an electron microscope, you will not see where the seam is. That's the whole point. Diffusion bonding, awesome technology. And that's what happens inside this hip. So fundamentally, on a molecular level, you can start something with like 80% good, but it's not that strong because at the moment you put stress, it will crack. But once you send it through that, again, mass does not change, size barely changes, and then you send it to turbine jet engine, it's like, bruh, I got this. I got this. Because of the quality improvement. And it's like night and day difference. Like that was very clear. It's like, oh, a little bit 10%, na. Night and day difference happens. And then you have control cool down. Generally, you will have normal cool down, but certain alloy requires gas quenching. Basically, you go. Now, gas quenching would be required if you want to lock in microstructure. Certain alloy creates a certain unique, basically alloy structures, and that is like, now we need to protect that. That gives you certain property that you are looking for. You're like, okay, we're gonna do gas quenching, but that's rare. Let that be clear. Not every machines have that, and this has to be done for every alloy that you sent into it. Ceramic alloys will have different one. Aluminum alloys will have different. Platinum will have different. But somebody has to sit down and calculate all of these things. Like some of the pressure vapors are small, so they generally have on top docker. Some are so huge, they're like, yeah, it's cheaper to do it from bottom somehow, but that's also done. So let there be clear, it's not a, oh, to put things in and done. Half of the R&D cost goes into figuring out this curve. The machine is dumb. Machine is not complex, but you need to figure out this curve. That takes time, lot of time, and lot of trials and error. Now we understand the future implication of this. This is what we call a critical technology. Basically, if your country wants to be like, superpower or like really, really good, it has to have this. Like, this is not a optional technology. Like, you have to have it. You can survive without lithography. You can't make nukes without it. So it has to be there. And here's the deal. You might be like, okay, what sectors utilize that? Answer, all. Like, again, let that be clear. Not everything you utilize in your daily life goes through this, but things that make your things do go through this. So fundamentally, every field uses it. Like defense, duh. Medical, duh. Jewelry, which again, I genuinely hope somebody in India is doing that, but platinum jewelry is also, people do that because again, if you have a ring, you want it to be very voidless. Benefit of that is like it's a much higher quality, it lasts much longer, the shine lasts. Basically, you can have the two rings, almost same amount of mass in them. But once that has gone through the HIP process, it will last much longer. Like genuinely, it will like, and it's actually can handle dents and stings better because again, there is no cracks that can expand because there is no void. So, and medical, again, you want to put something inside human body that has to be the best possible. So, the defense, the list is endless. Now, again, defense generally, because certain things are so big that they're like, yeah, we have to use forging. So that's why you will see the barrel many times are forged rather than hipped. But if you're talking about ICBMs, many of the ICBM stuff is hipped. So it's not a core system. Like you're not supposed to, this makes thing. This is a cooker. Basically, it turbocharges your other manufacturing system. Meaning, if you have a country that is smart and you have like a lot of good infrastructure for printed powder part, this is like, I got this. I can take your printed powder parts and like, why would you do this rather than like forging or cutting it out of a giant sheet metal? Powdered sheet metal is much faster than any system. And once you can cook it through this, it becomes as strong as a forged part. So you get best of both worlds, assuming you can afford this. And it's inherently not expensive. It's just robust. Like you need like big stuff. So again, powdered metal goes exponentially better. Then you have talking about basically machined part, that also goes there. Cast part, that also goes there. Forging, again, if you had got the main structure fixed, sometimes people will still send it there because it will solve all the unsupported access. So that's it. Basically, it takes your manufacturing and it turbocharges. It's like, I got this. And then you have 3D printing. With 3D printing will not grow as much as it is growing without this. Because again, now modern, basically jet engine turbine blade has like, a very complex air path. So, be mindful, whenever we say cooling air here, cooling air is actually 300 to 700 degrees Celsius. So, let that be very clear. Cooling air is relatively cooler. So, the outside temperature would be 1500 degrees C. The air that is coming that is cool, that would be 200 or 250 degrees C. So that cooling air, now again, this requires a very complex path. So 3D printer can make it, it's just that it won't be strong enough. You put in turbine, the moment it reaches high RPM, it just go kaput. So you take this, you put it in this tub and you cook it. The moment you do that, it becomes god tier. Like at that point in time, you do not discuss about this, like done, the end, go home. So are there any technology that exceeds this? There is only one, and it's so idiotic that we don't generally use it for many things. It is single crystal growth. Basically, how you have silicon grown like an ingot, same thing can be done with metal also. But again, it's very rare. If you like, If you are Tony Stark level rich, then only you can do that. Some things have been done with that, but expensive AF. And that's the only thing that has higher power to weight ratio compared to this system. But again, they are stupendously expensive and slow. And again, if you're talking about a nation, you need speed. This thing is a dumb process. It's like a bigger tub, or you can have multiple smaller tubs, go YOLO on it. So it's a very important technology. If you want your country to really, oh, we can 3D print it. No, we can 3D print anything. This is required. 3D prints basic stuff? Nah. 3D printing a rocket engine that's like, I got this. It has to be cooked. And once you can figure this out, and again, inherently nothing expensive is required. It's just robust, like really, really idiotically overbuilt parts. So this was my presentation of HIP. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, urge you to press dislike. Press it twice to show me disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.